In this video, I'm going to look at the systematic naming of some simple organic compounds. To make sure that all scientists around the world can communicate effectively, the naming of these compounds is governed by a set of rules which have been drawn up by the International Union of Pure and Applied Chemistry, otherwise known as IUPAC. To keep this fairly straightforward, this video will consider compounds that consist only of carbon and hydrogen, and these compounds will not contain any double or triple bonds. These compounds are known as alkanes. Here's the simplest alkane, methane. It consists of a single carbon atom bonded to 4 hydrogen atoms. The next simplest consists of 2 carbon atoms joined by a single bond, with the remaining available bonds around each carbon having a hydrogen atom. This is called ethane. The third is called propane and consists of 3 carbon atoms and 8 hydrogen atoms. Notice how these words are formed. Each compound's name ends in ane, which is also the way that the name of this class of compounds is spelt. The first half of the name tells you how many carbon atoms there are in the molecule. There's no easy way to remember these, they just have to be practiced and learnt. Here are the names of the first 10 simple alkanes. Some of the prefixes should be familiar from geometry. Note that these compounds follow a general formula which can be written as CnH2n plus 2. Now at this point I want to look at how these molecules are depicted, and I'm going to use butane, C4H10, as my example. One way of drawing these molecules is to include all the atoms and the bonds between them. This shows the complete structure of the molecule and hence is known as a structural formula. Note that this is a 2-dimensional representation of a 3-dimensional molecule, and hence the bond angles are not correct. The molecule has, in effect, been iron flat. A more easily written version is the condensed structural formula. This still contains all of the atoms but doesn't show the bonds between them. The reader is left to deduce those themselves. Note that the condensed structural formula has 2 CH2 units in the middle. This means that this representation could be condensed even more. Fortunately, this is still known as a condensed structural formula. Our last method is completely different. Instead of providing the atoms and expecting the reader to deduce the bonds, this method does the exact opposite. Only the bonds are drawn. Where bonds, shown as lines, join or end, a carbon atom exists. Carbon-hydrogen bonds are not shown, and carbon-carbon bonds are shown as lines. Atoms of other elements would be shown as their elemental symbols. This is known as a skeletal formula. Now, so far our molecules have been linear. The carbons have been arranged in a line. However, this is not always the case. For the time being, let's stick with our formula of C4H10. Here's what we've already seen, butane. However, there is another way of arranging these atoms. We can have 3 carbons in a chain, so this molecule is based upon propane. We call the longest chain of carbons the parent molecule. But then we have the 4th carbon off to the side. We call this a branch. This branch has only 1 carbon. An alkane with only 1 carbon would be called methane, so this branch is called a methyl group. So the name of our molecule is methylpropane. Now the IUPAC rules state that we must specify where the branch occurs, and we do this by numbering the carbons in the main chain. Now in this molecule the branch occurs on the 2nd carbon, so the full systematic name of this molecule is 2-methylpropane. Obviously branches aren't just limited to methyl groups. Similar names are used for branches with 2, 3, 4 carbons being called ethyl, propyl, butyl, etc. Molecules with the same molecular formula but a different arrangement of atoms are called isomers. Butane and 2-methylpropane are isomers. Because the difference between them is their different structures, these are called structural isomers. The structural formulae of these compounds show the difference between them. These are the simplest alkanes to be structural isomers of one another, so they avoid some of the other complications that can come about. To illustrate these, I'm going to look at the isomers of C6H14. Let's start with the straight chain molecule. This has 6 carbons in a long chain, so this is called hexane. To form the first isomer, I'm going to take a carbon and its associated hydrogens off the end of the molecule. This leaves a chain with 5 carbons in it, so the molecule that is about to be formed will be based on pentane. We can't add the methyl group to the end of the 5 carbon chain because that just reforms hexane. So let's add it to the second carbon. This forms 2-methyl pentane, our first structural isomer. Now, if adding the methyl group to the second carbon yields a structural isomer, we can do the same by adding the methyl group to the third rather than the second, to form 3-methyl pentane. It's tempting at this point to say we can have 4-methyl pentane, but look what happens if we number the carbons from the other end. It becomes 2-methyl pentane. This leads us to another rule. If there are 2 ways of describing where a branch is situated, we always use the lowest number. In this case, we would always describe this molecule as 2-methyl pentane, never as 4-methyl pentane. So far, we have 3 structural isomers with the same formula: hexane, 2-methyl pentane, and 3-methyl pentane. We need to check if there are any more. Clearly, we've gone as far as we can with a single methyl group as a branch. What about if we have 2 methyl groups? If we use 2 carbons as branches, that leaves us 4 carbons from our formula of C6H14. That means our parent molecule is butane. We can put both of our methyl groups onto the second carbon in the chain. This yields 2,2-dimethyl-butane. We can move one of the methyl groups onto the third carbon to give 2,3-dimethyl-butane. Like before, we can't have 3,3-dimethyl-butane because this is the same as 2,2-dimethyl-butane. Presumably, another possibility is for the 2 carbons we have used so far as separate methyl branches to also be used as a single 2-carbon branch, an ethyl group. Let's see. As before, our parent compound will have 4 carbons in it and hence be butane. Let's put an ethyl group on the second carbon. Now this looks tempting, but remember that the parent compound is the one with the longest chain length. This might not be in a straight line when drawn. This compound looks like 2-ethyl butane, but is in fact 3-methyl pentane. So, a simple formula like C6H14 can be 5 different molecules, all with subtly different chemistries. The number of structural isomers increases rapidly as a function of the number of carbon atoms, leading to a huge range of compounds. The world of organic chemistry is vast. However, it is these simple molecules that power our world, providing the fuel that drives our trains, planes, and cars.